Let's continue our discussion on rigid bodies. Last time we were looking at transformation matrix, and as I have said on previous occasions, whenever we see a matrix, we should immediately ask about what its determinant is, what is its trace, what are the eigenvalues, eigenvectors, and such questions we should ask. Okay, and that's what we are going to do in this video. So I will give a subtitle to this just to emphasize that such questions we should be asking. Determinant. Okay. Trace. Eigenvalues, eigenvectors, and all that. Okay. Okay, let's see whether asking about such things gives us some more information. Now, first thing we know about our transformation matrix is that it is orthogonal. Okay, A transpose is 1 or unit matrix. Okay, it's orthogonal. Second thing we have already found is that the determinant of A is unit. Okay, it's 1. And let's see what we can conclude from these two properties of this matrix about the eigenvalues and eigenvectors. That's what I want to do in this video. Also remember that A is a real matrix. Okay, it has no complex entries. Okay. Now I want to make the following claim. So I write following statements are true. So first is that if V is an eigenvector, you can put it in boldface if you wish. If I will not put, I'll put it only once. If V is an eigenvector, meaning it's a column, okay, which satisfies the eigenvalue equation, V is an eigenvector, then V star is also an eigenvector. Okay, meaning that if you solve the eigenvalue problem and you have found, let's say, one vector, then you can close eyes and say, if I take the complex conjugate of this vector, that will also be an eigenvalue of matrix A. Okay, so that is claim number 1. Claim number 2 is if lambda is an eigenvalue, then lambda star is also an eigenvalue. Okay, in fact what is true is that if lambda corresponds to V, then lambda star corresponds to V star. Okay, also we will show that all the eigenvalues, let's call them lambda I, where I will run from 1 to 3, they all are unimodular, meaning if you take a mod square, which is same as lambda I star lambda I, then this is 1. Okay, star is for complex conjugation. And we will also conclude that one of the eigenvalues is unity. Okay, so at least one of the eigenvalues is 1. Okay, so let's try to see that if these are true. Let me also tell you that for these, all I will need is that matrix A is real. Okay, and then okay, maybe this is fine, but it will be better if I tell you from what these things are following. We'll put it later after we have derived it. Okay, so let's do it this way. Okay, so let's look at what we get from determinant 1 condition. So I'm going to use determinant of A is equal to 1. Okay, so you take your matrix. Even before I do determinant thing, let me just I skipped a bit, jumped a bit. So first things first, let's say V is an eigenvector corresponding to eigenvalue lambda. So this is true. Then if I take complex conjugate, okay, then I get A star, but A is real, so A star is same as A, so I get A, and V star. On the right hand side I get lambda star V star. So you see, if V is a eigenvalue, then V star is an eigenvalue with a is an eigenvector with an eigenvalue lambda star. Okay, so that's our claim number. Let's go back. Which one was it? First two, A and B, I have proved now. Okay, and then let's do the following. Let's use orthogonality. So here I have used reality. Orthogonality. Okay, so I have one relation this. Let me do a transpose of this equation. So right now you have a matrix multiplying a column. I want to turn it into a vector multiplying a matrix. So if I take a transpose of this, it will give me V star transposed, which just means a row vector, times A transpose is equal to lambda star. This is a constant, there is nothing, it's not a column or something, so there's nothing to happen to this. And then you have V star transpose. Okay, and I will take this one and multiply with this equation. So what do I get? I get V star transpose A transpose, and then you have from here AV. Okay, now let's look at right hand side. Lambda star V star transposed, and I have to multiply the right hand side of this one, so I get lambda times V. Maybe I can multiply lambda here and V here. This is modulus of lambda square times V's, let me call it modulus of V square. Okay. Now what is this here? This is 1 because it's orthogonal. So on the left hand side also you have modulus of V square. Right hand side you have mod lambda square V square. And from this you can conclude that all the eigen values are unimodular. Okay, they all have magnitude 1. Okay, so this is my which claim? This one. This follows from A transpose A is equal to 1. Okay, that's nice. Now let's come to the last claim. Now determinant is 1, and if I diagonalize my vector A, then it's after diagonalization my A will go to a diagonal vector. Let me call AD with the subscript D. Okay, and this will have this form: lambda 1, lambda 2, lambda 3. See, this is 3 cross 3 matrix, so it will have 3 eigenvalues. Okay. Now if I find out the determinant does not change under a similarity transformation, and a similarity transformation takes you to its diagonal form. So the determinant of A will be the same as determinant of A diagonal, which will be lambda 1 times lambda 2 times lambda 3. Okay. Now go back to this one, not here, here. This relation implies that all the eigenvalues lambda i's, they all have this kind of form, e to the I alpha, with some alpha there. Okay, I can put a subscript alpha I, or maybe I just remove this subscript. So lambda is e to the I alpha. So lambda 1 will be e to the I alpha 1, lambda 2 will be e to the I alpha 2, lambda 3 will be e to the I alpha 3. Okay, so in that manner. Now let's say lambda 1 I choose to be e to the alpha, I alpha. Then one of the two, lambda 2 and lambda 3, has to be e to the minus I alpha. Why? Because I've already said that if lambda is an eigenvalue, then lambda star is also an eigenvalue. So if e to the I alpha is an eigenvalue, then e to the minus I alpha also has to be an eigenvalue. Okay. So let me call the one which has a value e to the minus I alpha as lambda 2. Okay, that is what I choose to call it. Then we have this relation, and my determinant of A should be 1, and I have these two, which means that lambda 1 into lambda 2 into lambda 3, 1 implies e to the I alpha, which is lambda 1, e to the minus I alpha, which we have chosen for lambda 2, times lambda 3 is equal to 1. Okay, and from this you can conclude that lambda 3 is equal to 1. So at least one of the eigenvalues is unity. And of course, if you take alpha 2, if alpha 0 is allowed, then all of them are unity, and so forth. Okay, but our interest in saying that at least one of them is unity, which means the following. If you take your vector A, then there is one vector which I call, let's say, R. So the V, one of the V's I am calling R, the eigenvalue. It has unit eigenvalue. Okay, so it's basically AV is lambda V, where lambda is 1, and V I am calling R, just to give it a name. Okay, or AR is R, meaning there is a vector R which does not change at all under the transformation. Okay, so when the matrix A, or when the rigid body is moving in whatever fashion it is moving, and you look at the matrix A, which takes takes the rigid body from its initial configuration to the final configuration. Okay, this equation is saying that there is a vector which does not change under all these transformations. Okay, there is one such vector. The effect of A on R is to do nothing, which means that R is an equivalent of the direction of rotation. You see, when you rotate a body about some axis, all the points on that axis do not move at all. All other points which are not on that axis, they go from here to there. Okay, they rotate by some angle, but the points on the axis of rotation do not change. So that vector which is aligned along the axis of rotation, that does not get changed. So I can conclude that the entire effect of matrix A can be thought of as a rotation about some axis, and the direction of that axis is given by R. Is it clear? So I can conclude effect of A is equivalent to a rotation about an axis. Yeah, and this is called Euler's theorem. Let me write it down. It's a nice result. I don't think it's it's obvious immediately why this should happen. I don't think it is trivial to say that, in whatever fashion you have moved around your rigid body, remember one point has been always fixed. Okay, it has a fixed point, and this entire from one orientation to another orientation is equivalent to a rotation about an axis. Okay, so this is a nice result, which also means that I should be able to do the following. You see, if you say that the entire effect is equivalent to a rotation about an axis by some angle, let's call it alpha or phi, we'll call it phi. Okay, so the entire rotation is equivalent to, the entire transformation is equivalent to a rotation by an angle phi. Okay, or maybe capital phi, probably, whatever, doesn't matter, angle phi. Then look at that matrix which does this rotation. It's just, if you take the axis of rotation to be the z axis, okay, then it will be just cos theta sin theta minus sin theta cos theta, right? So if you orient your axis properly, then the matrix will be equivalent to this: cos phi sin phi, I didn't mean theta, I meant phi, minus sin phi cos phi, and we are saying we will choose the direction of r to be the z axis. Then this is the matrix which does the rotation, right? Which means that I can go from A to this one by a similarity transformation, right? See, this is the one which does all the job, but we are saying whatever it does is equivalent to this rotation. So means I should be able to find a similarity transformation from here to there, okay, which will be equivalent to a rotation about the new z axis. Okay, that's good. Now how should I find out phi? See, I can find out the direction about which that rotation has to happen by solving the eigenvalue equation, right? So I find out that vector r by solving the eigenvalue equation. Now how do I find out the angle phi, the amount of rotation that is needed? Okay, and that's easy, because you know that the trace does not change under similarity transformation. Okay, so if trace does not change under similarity transformation, then lambda 1 plus lambda 2 plus lambda 3 should be same as cos phi plus cos phi, which makes it 2 cos phi plus 1. Okay, so I have added up the diagonal entries here, and these are the diagonal entries of A diagonal. Okay, now your lambda 3 was 1, so this cancels with this. Lambda 1 and lambda 2 were e to the I phi and e to the minus I phi, which makes it 2 cos phi. Okay, which means, sorry, 2 cos alpha. So on the left hand side you have e to the I alpha plus e to the minus I alpha, which is equal to 2 cos alpha, which means that phi is same as alpha. Meaning, when you find the eigenvalues, okay, the alpha that you get is this phi, right? So that's how you find the angle of rotation also. Okay, let's see what else I wanted to say. Okay, very good. So I want to leave you with a question. It looks like I cannot diagonalize this. Looks like I cannot diagonalize the matrix A because I have this, right? It's a rotation matrix, it's not a diagonal matrix. But some time back I said that I can diagonalize, and I have this one. Okay, I had all the entries as diagonal entries. Somewhere I should have written down here, lambda 1, lambda 2, lambda 3, and then you have cos phi, all these things. Okay, so these are two things, and then you also realize that eigenvalues are complex, e to the alpha and e to the minus alpha. I would suggest that you think for a while and be sure that you are completely sure about all these different parts fitting together nicely in your understanding. That on one hand, it looks like it cannot be diagonalized because it is having this form. On the other hand, you already know it is diagonal. Okay, just make sure it fits in all nicely in your understanding. Okay, so we'll continue further in the next video.